There is a thought that crosses almost every human mind at the moment of waking, that slow dissolve from vivid experience back into the familiar geometry of a bedroom ceiling, a thought that arrives like a quiet dismissal. It was only a dream. 4 words that carry within them an enormous assumption, an assumption so deeply embedded in the way we have been taught to think about consciousness and reality that almost nobody stops to interrogate it. That assumption is this: waking life is real, and everything that happens inside a dreaming mind is fundamentally, categorically not real. It is noise. It is biological static. It is your brain shuffling memory files in the dark. I want to spend the next several minutes dismantling that assumption at its foundation. Not through philosophy, not through speculation, but through the hard, rigorous, mathematically verified architecture of quantum mechanics, through the profound and deeply unsettling implications of the many worlds interpretation, and through what modern neuroscience is beginning to reveal about what the brain actually does when the relentless flood of sensory input finally goes quiet. Because here is the thing: the story physicists have been telling since 1957, a story backed not by poetic intuition, but by the cold, uncompromising language of mathematics, is that the universe you are currently occupying is not the only one. It is one branch among an unimaginably vast, continuously branching structure of physical realities, all of them equally real, all of them containing their own version of matter, energy, and time. And when you understand that story in its full depth, the question you begin to ask is not whether dreams are real. The question becomes whether sleep might represent something far more astonishing than a biological maintenance window. To understand any of this properly, we have to begin at the smallest scales of physical reality, at the level where the universe stops behaving the way your intuitions expect it to and starts behaving in ways that have baffled, thrilled, and quietly terrified the greatest physicists of the last 100 years. At the subatomic level, particles do not possess single definite properties before they are measured or observed. An electron traveling between 2 points does not take one path. It takes every mathematically permissible path simultaneously. Its position, its momentum, its spin, none of these are fixed values sitting quietly in space waiting to be discovered. They exist as a superposition, a vast overlapping wave of probability amplitudes described by what physicists call the quantum wavefunction. This wavefunction is not a metaphor for our ignorance. It is not a placeholder we use because our instruments are insufficiently precise. It is the actual physical state of the particle. The mathematics are unambiguous. The probability wave is the reality. Now, when that particle interacts with something, when it collides with a detector, when it is absorbed by an atom, when it becomes entangled with another particle, something happens to that wave function. In the older Copenhagen interpretation of quantum mechanics, the wave function was said to collapse. All those beautiful overlapping probabilities would suddenly reduce to a single outcome. The particle would be found here or there with a probability determined by the shape of the wave, and all other possibilities would simply vanish. For decades, physicists accepted this and moved forward because the predictions were astonishingly accurate. But there was always a discomfort underneath. Where did the other possibilities go? What physically caused the collapse? Why did measurement of all things have such a privileged role in determining the structure of reality? These were not merely philosophical inconveniences, they were deep structural wounds in the theoretical framework. In 1957, a young physicist named Hugh Everett III sat down and proposed something radical. He proposed that the wave function never collapses. Not ever. Not under any circumstances. What we interpret as a collapse, what we experience as a single outcome emerging from a quantum event, is not the elimination of the other possibilities. It is the splitting of the entire universe into separate, non-communicating branches, each one containing a physically real version of the outcome. Every quantum event, every interaction between particles at the subatomic level, every moment in which probability resolves into something measurable is simultaneously a moment of cosmic branching. The universe is not selecting one outcome and discarding the rest. It is instantiating all of them in parallel in what mathematicians call Hilbert space. Hilbert space is not a location. It is not a place you could travel to, even in principle. It is a mathematical structure of potentially infinite dimensions, and the different branches of the wave function exist in what physicists call orthogonal dimensions within it. Orthogonal, meaning they do not intersect, they do not bleed into one another, they cannot communicate by any classical physical mechanism. Each branch is sealed from the others by the structure of the mathematics itself. This is the many worlds interpretation, and it is not a fringe idea. It is taken seriously by a significant portion of theoretical physicists working today, including figures like David Deutsch, who has built an entire framework for the theory of computation and the philosophy of knowledge on its foundations. The alternate timelines are not science fiction. They are the natural, mathematically necessary consequence of taking the wave function seriously as a description of physical reality. Now hold that picture in your mind, an incomprehensibly vast structure of branching physical realities, each one as real as the room you are currently occupying, sealed from one another by the geometry of Hilbert's space. And then ask yourself why you only ever experience one of them. The answer lies in a process called quantum decoherence, and it is perhaps the single most important concept for understanding both why we experience a single classical reality and why that experience might not be the complete picture. Decoherence is what happens when a quantum system becomes entangled with its surrounding environment. When you are awake, your brain is not sitting in isolation. It is being continuously bombarded. Photons from every light source in your environment are striking your retinas hundreds of trillions of times per second. Air molecules are colliding with your skin and eardrums in an unceasing cascade. Temperature gradients, pressure variations, the constant electrostatic and gravitational field interactions that saturate any physical environment, all of these represent a relentless, high-bandwidth stream of physical information flowing into your biological neural network from the immediate classical world. Each one of these interactions is, at the quantum level, an entanglement event. Your neural architecture is becoming continuously entangled with the surrounding environment. And what that entanglement does, mathematically, is force the quantum wave function describing your brain's physical state to lose its coherence across different branches. The probability amplitudes that describe alternate possibilities lose their ability to interfere with one another. The quantum superposition that might otherwise allow your neural processing to sample across multiple branches of the wave function is rapidly, continuously, and completely suppressed. This is decoherence. It is the mechanism by which the classical world emerges from the quantum substrate. The environment acts as a constant measuring apparatus, and that continuous measurement collapses, or more precisely, suppresses the coherence of the quantum possibilities available to your conscious neural processing. You are locked irrevocably and completely into one branch. You perceive one timeline, you experience one history, not because that is the only history that physically exists, but because the environmental decoherence is so overwhelming, so total, so relentlessly efficient that no signal from any other branch can reach you. Think about it this way. Imagine a highly sensitive radio receiver sitting inside a massive industrial factory. All day long, a powerful, localized broadcast tower blasts a single dominant station directly into the receiver at overwhelming volume. The other broadcasts are real. They are propagating across the landscape from dozens of neighboring stations. Their electromagnetic signals are physically present, passing through the walls of that factory. But the signal from the local tower is so intense, so completely dominant, that the receiver cannot detect anything else. You would naturally assume, listening to that receiver, that there is only one broadcast in the world. You would not be lying. From within the factory, from within the deafening presence of that local tower, there genuinely is only one audible signal. Waking consciousness is that factory. The sensory world is that local tower. The decoherence imposed by your continuous physical interaction with the immediate environment is so complete, so powerful, so total, that your neural architecture has no capacity whatsoever to detect informational resonances from neighboring branches of the wave function. But the factory does not run forever. Every 24 hours, it shuts down. Deep sleep is one of the most remarkable physical states that biological matter has ever achieved. During the deepest stages of the sleep cycle, sensory input drops to near zero. The eyes are closed and still. The auditory cortex receives minimal external signal. The olfactory and somatosensory systems go quiet. The motor system is actively paralyzed. And crucially, the constant high-bandwidth entanglement between your neural architecture and the surrounding classical environment drops to its lowest possible level. What does that mean for decoherence? If decoherence is driven by the rate of environmental entanglement, and if that rate collapses during deep sleep, then the quantum coherence of the neural wave function is no longer being continuously suppressed at the same overwhelming rate it experiences during waking life. The mathematical precision of this claim requires care. We are not saying that the sleeping brain becomes a quantum computer in the full technical sense. The thermal noise of biological tissue, the sheer complexity and scale of neural systems present formidable barriers to maintaining quantum coherence even in the absence of external input. These are real physical obstacles that no honest theoretical framework should ignore. But consider what the brain is doing during dreaming sleep. It is generating rich, detailed, spatially coherent, temporally structured experience in the complete absence of external sensory input. The visual cortex is active. The hippocampus is active. The prefrontal regions that govern logical consistency are partially suppressed. The brain is, by any reasonable description, running an internal model of a reality that is not anchored to the external classical world at all. It is processing information about a physical environment that its sensory systems are not currently reporting. Where is that information coming from? The standard neuroscientific answer is memory consolidation, pattern completion, the associative firing of neural networks as they reorganize and strengthen synaptic connections. And that answer captures something real and important, but it does not capture everything, because the experience of dreams is not merely a replay of stored memories. It involves novel configurations of information, new environments, unfamiliar people, physics that does not always obey classical rules, encounters with versions of reality that do not map cleanly onto any single remembered experience. The theoretical framework that the many worlds interpretation opens up is breathtaking in its implications. If the brain's quantum wave function, partially freed from the relentless decoherence imposed by waking sensory bombardment, achieves even a transient and partial mathematical resonance with the broader probability structure of Hilbert space, then the information appearing in dream consciousness might not be arbitrary noise. It might be faint, overlapping, imprecise informational reflections of physical states that exist in neighboring branches of the wave function. Your dreaming brain might be, in a mathematically precise sense, catching distant transmissions from parallel physical realities. The geometry of Hilbert space does not permit classical communication between branches. You cannot receive a message from a parallel version of yourself the way you receive a text message. The orthogonality is total at the classical level. But the quantum wave function, before decoherence fully suppresses its coherence, does contain amplitude contributions from multiple branches simultaneously, and a neural system whose coherence suppression has been significantly reduced might, in principle, process information that carries the mathematical fingerprints of those alternate branches. This is not a claim that your dreams are literal windows through which you are watching another universe in real time. The filtering and distortion introduced by biological noise, by incomplete decoherence suppression, by the reconstructive nature of neural processing, would make any such signal unrecognizably transformed by the time it emerged as conscious experience. What you would experience would not be a clean, high-definition broadcast from another timeline. It would be fragmented, overlapping, emotionally charged, spatially unstable, precisely the phenomenological signature we associate with dreaming. Consider, too, the extraordinary consistency with which certain dream experiences repeat across human beings, across all cultures and all recorded history. The experience of impossible flight, the experience of falling, the experience of moving through a familiar place that is simultaneously wrong in some deep structural way, as though it is both a place you know and a place you have never been. The experience of encountering people who are simultaneously familiar and completely unknown. These are not the signatures of random neural noise. They are too consistent, too universal, too structurally coherent to dismiss as meaningless static. The universe, in its deepest mathematical structure, is not a single thread. It is a vast, continuously ramifying tree of physical realities, every branch as real as this one, every branch containing matter organized into stars and planets, and, in at least some of those branches, minds. And those minds, like yours, are embedded in a biological architecture that evolved inside one branch of that tree, anchored there by the relentless, efficient machinery of environmental decoherence. But for a few hours every night, the machinery slows, the anchor loosens, the factory goes quiet. The question that the mathematics of quantum mechanics places before us, quietly, without drama, with the cold precision of a wave equation, is not whether there are other realities. The mathematics resolved that question decades ago. The question is whether the sleeping brain, that extraordinary, ancient, improbably complex information processing system, is doing exactly what a sufficiently sensitive receiver would do when the local tower finally stops broadcasting, not hallucinating, not cleaning house, not generating noise, tuning in,